All right, now we're going to talk about circular motion dynamics. Our previous video was about the kinematics of circular motion, and now we're going to get into forces. So anytime there's acceleration, we know that there must be a force in the same direction. The centripetal force is also center pointing, just like our acceleration, and is given by the sum of the forces, or your centripetal force, is equal to the mass times the centripetal acceleration. You could also say that centripetal force is equal to the mass times the velocity squared divided by r. And this is from substituting in one of our equations for centripetal acceleration. We can substitute in another equation that we have for centripetal acceleration and get the mass times 4 pi squared r divided by the period squared. So we have three equations for centripetal force, which is kind of nice. It seems like we've got a lot of extra stuff here, but really what it does is it helps us say we're only given period, mass, and the radius. We can go ahead and use this equation, and we don't have to go through lots of extra steps. Otherwise, if we already have the centripetal acceleration, we can go ahead and just use F equals ma. So some examples of centripetal forces. A mass is twirled in a circle at the end of a string. The centripetal force is provided by the tension in the string. So that center-seeking force, it's provided by the tension in the string. When a car rounds a corner on a highway, the centripetal force is provided by friction between the tires of the car and the road. And when the moon circles the Earth, the centripetal force is provided by gravity. Again, you have this gravitational force pointed from the moon toward the center of the Earth. That is equivalent to your centripetal force. So kind of cool thing about this with free body diagrams is if you're looking at a free body diagram and you have something moving in a circle and there's any sort of inward force that you can see pretty clearly on your free body diagram, say gravity, for example, it's pretty easy to go ahead and set that equal to your centripetal force. Centripetal force is not an inherent force of the universe like gravitation is, but it's the sum of the forces acting on an object which is undergoing uniform circular motion. That's why in our equation back here, I listed it or wrote it as the sum of the forces or sum of centripetal force. It's the sum of the forces. It's a net force. Okay. It results from one or more forces such as gravity or tension or friction. So again, it's going to be really important that you draw free body diagrams and that you pay attention to which forces you have going in which directions. Quick note on centripetal versus centrifugal. Centripetal force means center pointing. It is a real force. It is something that we can use and work with. It exists. Okay, it's the sum of those forces acting on an object going in a circle. Centrifugal, on the other hand, means center fleeing or pointing outward. It is fake. It's a fake force. And a good way to remember this is that the F in the word, fake starts with F, so the F in the word can help you remember that centrifugal fake force is a fake force. The outward pull, so you might have been in a car and you feel yourself when you're going around a corner or something, you feel your body being thrown toward the outside of that turn. And so a lot of people, they want to say that it's centrifugal force that's doing this. Well, remember, centrifugal force is a fake force. What's really happening is that outward pull you feel in a turn is due to inertia. Your body wants to keep going the same direction it was going before. It wants to keep going tangent to that circle, that curve. But the car is pulling you toward the center of the circle. So there's a centripetal force with the car pulling you toward the center of the circle, but there's also inertia throwing your body outward in the direction that it wanted to travel. So be careful with that. Do not use the word centrifugal. It is a fake force. We want centripetal, center pointing. I have some examples that you can try on your own in class. They're just plug and chug where you're substituting values into our force equation. So you can go ahead and do those. We're not going to cover unbanked and banked curves this year just because of our lack of time. But if you would like to cover those on your own, I highly recommend doing it for the AP exam. And if you have questions, again, please let me know and we will get together and do a meet. All right, that's all I have for you. Bye.